Before we discuss Charles' law, we want to make sure that we remember how we get Kelvin units for our temperature. So Kelvin scale is based on absolute zero equaling zero, meaning it's the temperature at which molecular motion ceases, and therefore we don't have any temperature if we don't have any movement of molecules. How do we get that? It would simply be by taking our Celsius temperature and adding 273 to that. Therefore, absolute zero would equal negative 273 Celsius. I hope you watched the awesome video with the liquid nitrogen on the class page showing Charles' law, where as temperature increases, volume increases, temperature decreases, volume decreases. So the direct relation that we see between volume and temperature has some important limitations. First of all, Charles' law only applies when the number of moles of a gas are held constant, so the amount, and that can simply be implied as an example of a tide balloon. We would know we would be putting no more air in or out. And then we also need to know that the pressure is being held constant. But most importantly, the temperature that we are looking at is in Kelvin units. If it is not, the direct equation that we're looking at here is not true. That's the sophomore mistake, forgetting to convert the Celsius temperature units to Kelvin before solving any problems. So let's look at our first problem. All right, so they are telling us that pressure is constant, and they are saying nothing about the amount of gas changing. So we know that with those two conditions holding, we can use Charles' law. So we're going to write V1 over T1 will equal let's change colors here, will equal V2 over T2. So let's find the corresponding variables in our problem. So we'll call condition 1 what they give us here at the beginning, the 100 centimeters cubed and the 200 Kelvin. And we'll call condition 2 what is the volume. We're being looked for that given 150 K. So big reminder, temperatures must be in Kelvin. They are in the way the problem was given, so that simplifies things. But we notice that our given volume is in centimeters cubed. They're asking for decimeters cubed, so we can solve for centimeters cubed and make that conversion at the end. But we want to start thinking smart. We see that the temperature is decreasing in this problem as we go from 200 Kelvin to 150. Because they are directly related, I know that volume must also be decreasing. So when I'm finished this problem, if I don't have an answer that is smaller than 100 centimeters cubed, I know I goofed somewhere and I go back and do it. Right, so let's plug our values in. So V1 is 100 centimeters cubed. T1 is 200 Kelvin. Remember that bottom temperature unit must be in Kelvin or the equation is not true. And we are solving for V2, that's our unknown, and T2 is 150 Kelvin. So you can solve this any way you like. I typically cross multiply when I do my algebra. So we'd have 100 times 150, and that would equal V2 times 200. Isolating and solving for my V2, I would get 75 centimeters cubed, and we want 4 significant digits. Ooh, you know what? I don't like just having one significant digit looking at that. So let's just go with the 4 using the 100. You know, looking at it, following all rules, I agree it would be 1. But we're going to use 75 centimeters cubed. Okay, now they want that in decimeters cubed. So let's think way back to September. Remember that a milliliter is the same as a centimeter cubed. A liter is the same as a decimeter cubed. And we know that 1,000 milliliters are in a liter, and 1,000 centimeters cubed are in a decimeter cube. So if we're going to take our 75 centimeters cubed and we want to put that in decimeters cubed, we're going to use this equality to help us out. So we'd have our 75 centimeter cubed, and we'd have 1 decimeter cubed over 1,000, and we would find that we would get 0.075 decimeters cubed as our final answer. Let's look at another example. So when we read the problem, we're focusing on clues to know what law we want to use. We see that pressure is constant. There's nowhere that it's implied that the amount of gas is changing. So we're going to use Charles' law. So we know V1 over T1 will equal V2 over T2. Remembering that volume for both set of conditions would have to be the same unit, and temperature, we're limited. It must be in Kelvin units. So let's think about what's happening here in the problem. First, let's find our first set of conditions. We have a volume at 473 centimeters cubed and 36 degrees C. And we're being asked, what will happen to the temperature if the volume increases to 562? So we see that volume is increasing. We know that temperature and volume are directly related. So we know here that our temperature must also be increasing. So when we solve this problem, we know at the very end, it's higher than 36 degrees C, or we made a math error somewhere. All right, so let's fill in our different variables. So for V1, we're going to have 473 centimeters cubed, and we need to convert our temperature to Kelvin. So that's going to be 36 plus 273 Kelvin. And that is going to equal 562 centimeters cubed. And we are solving for T2. Right? So this here, if we plug that in the calculator, we're going to get 309 Kelvin. So now we'll do our cross multiplication, and we solve and finally get that T2 would equal 367. Remember, that is Kelvin units. So the question, when we look back in the problem, says they wanted to know the temperature in degrees C. So degrees C is simply going to be Kelvin minus 273. So 367 minus 273, and that is 94 degrees C. And we look back. Our initial comment, we knew the temperature had to go up. It did. It makes sense. So at least our answer is logical. I also want to briefly touch upon Guy-Lussac's gas law. And his law states that if volume in moles of a gas are held constant, the pressure of a gas and the Kelvin temperature are directly proportional. So pressure goes up, temperature goes up, pressure goes down, temperature goes down. As an equation there, again, we can see that we're going to have to make sure that we put our temperature in Kelvin units. The hints, we're looking for constant volume. So what do we mean? Here we have to remember that it would mean it's a rigid container. So it couldn't be a balloon, something like an aerosol can. This is why it's so dangerous to leave an aerosol can somewhere where it's going to be exposed to high temperature. The gas, the temperature, as it would increase, the pressure inside would be increasing because the container is rigid. That pressure would eventually hit a point where it could possibly cause the container to explode. So that's all for today's lesson. Please check on the class page for the problems that correspond to this video lesson.